Let us talk some important points related to the thermodynamics. First of all, we'll focus on the intensive and the extensive properties which are depending on the amount of the substances. Now, when it is not dependent, do not depend, or simply the in stands for independent of the mass, we call this property as the intensive property. For example, the properties are like pressure or density or the concentration or the temperature. These are not property depending on the amount of substances. So we call these as the intensive properties. In case the extensive properties, these are totally depending on the amount of substance. Hence, we call this property as the extensive property, like mass or volume or heat, quantity of heat. All these properties are depending on the amount of substances. Now, the type of processes, we already know isothermal, where the temperature remains constant. So, we have to remember delta T will be equals to 0. Now, the temperature somewhere related to the internal energy of the system. So, delta U will also be equals to 0. In case of adiabatic process, the heat exchange will be constant. So we say Q is equals to 0. But in this case, remember, delta T is not 0. Delta U is also not 0. In case of isochoric process, the volume remain constant. So delta V is equals to 0. Somewhere we have a formula of W is equals to P delta V. Therefore, W will also be equals to 0. And here the heat exchange can also be equals to the internal energy. In case of isobaric process, where the pressure remain constant, so delta P is equals to 0, which is nothing but the Q is somewhere related to the delta H. So remember, for isochoric process, delta U is equals to the heat exchange at the constant volume, while delta H is the heat exchange at the constant pressure. For the cyclic processes, the series of changes of the state and finally returns to the initial state is called as a cyclic process, where the delta, that is state function, that equals to 0. So in short, delta V is equals to 0, delta U is equals to 0, and delta H also equals to 0. Reversible process, where the driving force and the opposing forces differ in infinitesimally small amount. So they are very slow process, hypothetical, ideal, non-spontaneous processes. Maximum work is obtained under the reversible process. Driving forces, and if the opposing forces they differ by the fixed amount, we call this as irreversible process, where the system and the surrounding are in equilibrium only in the initial and final state. They are comparatively fast, finite times of completion, practical, real, and the spontaneous process. No maximum work can be obtained during this. Now, some of the formulas we should remember for work done calculation. For example, for any irreversible processes, remember that's not a maximum work done. So, W is equals to minus P delta V. But in case of the reversible process, which is the formula for the W max, that's equals to minus 2.303 nRT log to the base 10 V2 upon V1, that's equals to minus 2.303 nRT log to the base 10 P1 upon P2. So volume and pressure can be related to the work using this formulas. Also, while doing all this calculation, you need to remember some of the conversions, like 1 liter atmosphere is converted into 101.3. This is the conversion term that we can use for converting liter atmosphere into the joule calculation. So 1 liter atmosphere, that's equals to 101.3 joule. Next is in case of internal energy. Internal energy is denoted by U, is actually consisting of two types of energy. One is the kinetic energy and one is the potential energy. When we talk about the kinetic energy, that's consisting of translation energy, then that's consisting of vibrational, or that's consisting of rotational energy, or that must be consisting of the electronic energy. In case of the potential energy, always remember this is something related to the intermolecular energy, or it is maybe related to the intramolecular energy, or maybe related to the nuclear binding. So these are the internal energy types that we have to remember. And magnitude wise, you always remember the trans is having more magnitude, then vibrational, then rotation, and lowest energy you will get it from the electron. Just MCQ point of view, you should remember this. Now, in case of first law of thermodynamics, we know all the statements that energy neither be created nor be destroyed, can be converted from one form to another form. Now, we have to focus on a mathematical form of this equation. Delta U is equals to Q plus W. Now, here, in case of different things, if the Q is positive, heat is absorbed, negative, heat is evolved. In case of W, if it is positive, then the work done on the system, and if it is negative, the work done by the system. Now, under different processes, how this equation is going to change, that's very important. For isothermal processes, the delta U is equals to 0, Q will be equals to minus W. For adiabatic process, Q will be equals to 0, therefore we'll write delta U is equals to W. Isobaric process, here delta P will be equals to 0, so W will be equals to minus P delta V, that will remain as it is. In case of isochoric, where the delta V is equals to 0, so W will also be equals to 0. So these are different formulas related to the first law of thermodynamics. Next, in case of enthalpy, we have a formula H is equals to U plus PV. If you calculate for the different state functions, we'll get a delta H is equals to delta U plus P delta V. This is a formula which is related to the work done. We can use it. But if the enthalpy of the reaction is to be calculated with respect to any chemical reaction, we have to use formula delta H is equals to delta U plus delta nRT, where the delta N is number of moles difference between the reactant and the product, provided the reactant and the products are present in the gaseous system. Little bit some information about each one of this term. For example, like enthalpy of formation. Enthalpy of formation is nothing but the enthalpy which is accompanying the formation of 1 mole of a substance in its standard state. So generally MCQ wise the question comes on the enthalpy of formation, that identify the reaction which is the enthalpy of formations. For example, if I have to identify the reaction for related to the methane formation, always remember there should be carbon plus hydrogen in their elemental state. Though I know the carbon and hydrogen can't react to give the methane, but always remember the enthalpy of formation reaction should always consisting of the product which is formed from its element in their standard state. So if I have to find out the equation for the H2SO4, I will write H2 plus S2 plus twice of O2, which is practically not possible, but this is the equation for the standard enthalpy of formation. So it is always remember the product has to be formed from the reactant in its standard state. Now next is the standard enthalpy of combustion, which is accompanying the 1 mole of a substance in its standard state when it is burned in excess of the oxygen or the air. You will find this enthalpy of combustion is always a negative, okay? But there are some reaction when the combination of oxygen will leading to the combustion where you will find delta H positive. So remember these two examples, N2 plus O2 giving twice of NO and F2 plus half of O2 giving OF2. Both these reaction where you will find delta H positive. So these are exception one. Otherwise, enthalpy of combustion you will always find the value to be negative. Enthalpy of neutralization. It's the enthalpy accompanying the neutralization of 1 gram equivalent of an acid by 1 gram equivalent of the base in the dilute solution. For the strong acid and strong base, always remember this enthalpy of neutralization will be always equals to minus 13.7. That's kilocalorie per gram equivalent, or that's equals to minus 57.32 kilojoule per gram. So this particular standard value will be always for the strong acid and strong base. Now the compounds with the positive value of this is for the strong acid and strong base containing H plus and OH minus. Next is a bond enthalpy. Bond enthalpy is nothing but the enthalpy change which is necessary to break particular bond. So if you are calculating the heat of reaction using the bond enthalpy, always remember it is heat of reactant minus heat of product. If I am calculating the enthalpy related to the enthalpy of formation, always remember delta H is equals to heat of product minus heat of reactant. So these are some formulas related to this we have to remember. Now just a quick revision of the definition. Heat of fusion, that's 1 mole of a substance. When it is melted, it's called as fusion. Enthalpy of vaporization, 1 mole of a substance or liquid which is vaporized is vaporization. Enthalpy of sublimation, 1 mole of a substance converted into the gaseous phase. Ionization is nothing but the removal of an electron from each atom from 1 mole of a gaseous substance. Electron gain enthalpy, it's a enthalpy related to the 1 mole of a gas when they gain electron in the outermost shell. And enthalpy of solution, that's a dissolution of 1 mole of a solute in around 1 liter of a solvent. We call it as the enthalpy of the solution. The next part that we'll be focusing, that's the heat capacity. Heat capacity is generally denoted by the symbol C. Heat capacity is nothing but the amount of heat which is required to raise the temperature of the system through 1 degree or 1 Kelvin. The unit of this is generally joule per Kelvin. Now this can be expressed in 2 different ways, that is heat capacity at constant pressure and heat capacity at constant volume. When I'm talking about the CP, CP is always equals to delta H upon N into delta T, while CV is always equals to delta U upon N into delta T. CP minus CV, that's equals to R. Also remember, the CP divided by CV is equals to gamma. If gamma is equals to 1.33, this is particular value we have to remember, the molecule will be triatomic. If it is 1.40, the molecule will be diatomic, and 1.66 for the molecule to be monoatomic. So these are the values which are to be remembered while calculating whether the substance is monoatomic, diatomic, or whether it is triatomic in nature. Now in case of the Kirchhoff's equation is nothing but delta H2 minus delta H1 divided by T2 minus T1 is equals to delta Cp. So this is nothing but it gives the effect of temperature on the heat of reaction at the constant pressure. Also remember delta Cp, it's a constant volume. This is something the formula which we can use when this particular Kirchhoff's equation is for the constant pressure. We can use it for the constant volume also, and there we can use delta U2 minus delta U1 upon T2 minus T1 is equals to delta Cv. So these are some Kirchhoff's equation derived formulas we can use. In case of Hess law, we know that whether the reaction take place in 1 step or the 2 step, the final heat of reaction is always a combination of different steps. For example, if I'm saying A is giving B, B is giving C. This is having delta H1 heat of reaction, this is delta H2. If I'm to calculate for A is equal to C, delta H, then delta H will be equals to delta H1 plus delta H2. That's the Hess equation. Most of the problems related to the Hess law can be asked. The spontaneous and non-spontaneous process, the process which occurs of its own, no external forces are required, we call it a spontaneous process, and the one which occurs or requires the external forces to occur, we call them as non-spontaneous. Now in this case, the entropy plays very important role. Entropy is nothing but the randomness. So solid, when it is turning to liquid and then it is turning to the gas, the entropy of system, that is disorderliness, is always increases. Entropy of the system is generally calculated by using heat reversible upon T. So it's directly proportional to the heat provided and inversely proportional to the temperature at which this system is already present. Now we can relate this entropy to calculate the spontaneity and the non-spontaneity of the system using the second law of thermodynamics. According to the second law of thermodynamics, the spontaneous heat flow is always unidirectional. That is, always the spontaneous heat flow will be from high temperature to the low temperature. In case of the heat cannot be completely converted into work without producing the permanent changes either on the system or on the surrounding. So no machine in the universe has the 100% efficiency. So delta S for the universe is equals to delta S of the system plus delta S of the surrounding. If this is greater than 0, if it is positive, then this reaction is said to be the spontaneous. So we have a rule to identify the spontaneity of system when the delta is total, that is system plus surrounding. If it is positive, the reaction is spontaneous in nature. But according to thermodynamics, the thermodynamic is always deals with the system, not with the surrounding. So this particular rules fails under the criteria of the thermodynamics. So we need a term which will only define the system, not the surrounding. And hence we have introduced a term that is Gibbs energy. So Gibbs energy is equals to delta G is equals to delta H minus T delta S. So we can use this particular formula. So if the delta G is a negative, the reaction is said to have the spontaneity. And if it is positive, the reaction is non-spontaneous. So we can have a different relation using this formula. So remember, if delta H and delta S, if both are negative, then the delta G will also be negative. So reaction will be spontaneous at all, that is comparatively delta H should be less than the T delta S. So this reaction will be spontaneous. Then delta H and delta S, if both are positive, then delta G will be negative only, and this reaction will be again the spontaneous, provided the T delta S has to be greater than delta H, while here the T delta S has to be less than delta H. Let's say if the delta H is negative and delta S is positive, then the delta G value will always be negative. So it's always spontaneous. And if this is delta H is positive and delta S is negative, delta G will be positive, and this is always non-spontaneous. This kind of questions can be asked related to the MCQ. So we have to remember this, how the spontaneity changes with respect to the Gibbs energy. Also related to the Gibbs energy, how we can equate it with the equilibrium. Always remember, delta G0 is equals to minus 2.303 RT log K. So equilibrium constant can be related to the delta G value using this equation. So you need this particular formula while solving the MCQs related to the Gibbs energy. Now the last additional points and some third law of thermodynamics. So third law of thermodynamics is something which is dealing with the entropy of the perfectly orderline crystal substance, which is always found to be 0. That is, S is equals to 0 if the absolute temperature is 0 Kelvin. So it's important, it allows to determine the absolute entropy of the system, because delta S is equals to, that is at S in that particular temperature, minus S0. But S0 is 0. At 0 degree S is 0, that's why that is equal to just ST. So that's entropy at the of the system at present at that temperature. So this is Cp dt upon T. Now additional information that you should remember for the solving MCQs. First of all, internal energy is the change is heat evolved or the absorbed at the constant volume, and it is found by using a bomb calorimeter. So internal energy can be calculated using this bomb calorimeter, which works with the formula, that is delta U is equal to C, that's heat capacity, multiplied by molecular weight upon weight of the substance into delta T. So this is the formula you will be using for the bomb calorimeter. Also the calorific values. The calorific values are generally for the fuel or the food is generally divided by calculating the heat in calories, which is obtained per by this you can say by combustion of 1 gram of that fuel or a food. So that heat evolved during that process to be calculated. Also, we have to remember for the Carnot cycle. Carnot cycle it's a cyclic system which returns to the original state after undergoing the number of successive changes. The most common example is the Carnot cycle. Just remember, in stage 1, it's an isothermal expansion. Then it's stage 2, that's the adiabatic expansion. Stage 3, it's isothermal compression, and stage 4, it's adiabatic compression. So finally the system comes to its original position where it's called as the cyclic process.